Okay, now let's talk about the nitty-gritty. Let's start talking about some of the mathematics of crypto. Okay, and cryptography today, most of them be symmetric, asymmetric. It uses the idea of modular arithmetic. And in short, modular arithmetic deals with finiteness. Okay, this is the idea of the modular arithmetic. So if you went to high school, you probably are familiar with both of the terms. Modular, where it uses the idea of the modulus, we basically use percentage, right, as a modulus operator, and it's arithmetic. So it uses this idea of the modulus to make things finite. So everything in crypto is finite, and all the algorithms are based on the finiteness. So what are finite and what are infinite? Well, infinite could be, let's say, I don't know, set of real numbers, right? They are infinite in nature. Or would have set of integers. Well, and just go on and on, right? Numbers can be all the way to infinite. So they do not fulfill the idea of modular arithmetic. Okay, for something to be in crypto, it has to be finite. So another simple example of it, okay, of finiteness would be our clock. See, a clock. So got this clock here. So got this 6, 12, 3 and 9, considering it's, let's say 12-hour format clock. Well, it is finite in nature, which means no matter what I try to add on the clock, okay, it's always gonna go back to being finite. That is, the option of would be, well, if you're using a 12-hour clock, it would be from 1, well, all the way to 12, right? So 1, 2, 3, all the way to 12, and after 12 it will go back to 1, and then just repeats. So this is finite. Well, for example, if you say, I'll say in 20 hours from now on, so let's assume it's 10 a.m. right now. So 20 hours from today doesn't mean it's 30 a.m., right? Why? Well, it's finite in nature. So considering this 12-hour clock, 20 hours from right now, okay, 10 plus 20 is going to give us, next day's 10 a.m. would be basically the addition of 24, but plus 20 would be basically 4 in there. So 10 minus 4 is going to be 6 a.m. Okay, which means if I say, oh, I'll see you in 20 hours from now on, considering it's 10 a.m. now, well, I'm talking about seeing you at 6 a.m. tomorrow. So this is an example of finiteness. Okay, and another example we can consider is numbers. We've got numbers in here, so all the way to numbers, let's say 8. Let's say we have total of 9 numbers, and let's try to do some regular operations in there. Okay, let's try to multiply the numbers within. Let's say I'm multiplying 2 by 3. Okay, it's gonna be 6. Well, 6 is within here, right? 4, 5, 6, 7 and 8. So, well, it belongs within. Or good, I don't know, say 4 plus 4 becomes 8. And believe it or not, 8 is also here. Well, it's looking like it's starting to be finite. Well, not really. So if I say 4 times 4, it's out of the equation. I mean, 4 is here, but 4 times 4 brings me 16, which is not here, which is out of our bound. Or another one would be, let's say 8 plus 2. Well, 8 plus 2 will basically give us 10. 10 is also out of the bound here. Well, what we can do is once it reaches the upper bound, we can always go back to 0, which means 8 is the highest bound here. So 8 plus 2 instead of 10, I could just start counting from here again, 0 and 1. So I could now write 1 in there. Okay. Another example would be, let's say 8 plus 4. So 8 plus 4, well, in our terms is 12, but it's out of bound, which means after 8 I can just add 4 from here. So 0, 1, 2, 3. So 1, 2, 3, 4, which means this is going to be equivalent to 3. Okay, so we're getting somewhere. That is, we're trying to make sure that even though it's going to be out of it, we always want to go back to being within this bound. And for that, after this biggest number we have here, 8, well, we started counting again from the start. And equivalent of 12 would be 3, equivalent of 10 would be 1, and we could basically keep on doing it. Well, it turns out this idea of having 3, this idea of having 1 is rooted within modular arithmetic. Okay, so it's nothing but a modulus 9, which means that the secret lies here on this modulus 9. So for example, this 8 plus 4, okay, well, it's going to give us 12, but if I perform a modulus 9, in the word, if I basically try to find the remainder of it, well, the remainder will be 3, which means, so 9 1 is 9, okay, 9 plus 3 is going to be 12, so 3 is the remainder. See, so if I try to divide 12 by 9, so 9 times 1 would be 9. Okay, the difference is the 3, and this 3 is my remainder, which means I'm using the modulus 9 operator in order to compute the value that belongs within this boundary, okay, from within this, from 0 all the way to 8. And in fact, for this one as well, I can divide it by 9. So 8 plus 2, well, it's going to be 10, but divide it by 9, it's going to give me the value of 1, right? So for 10, 9 times 1 is 9, remainder is 1. Anything that's going to do with modulus basically means getting the remainder. Okay, but there's a formal way of writing it, okay, and it's a little weird at first. So for this modular operation, we say let a, r, and m, where a is my number, r is the remainder, m is the modulus. Okay, if let a, r, and m, okay, belong to the set of integers, okay, where this represents the set of integers, and let's say m is greater than 0, make sure that, you know, anything that's being dividing is greater than 0, then we can write it as a is equivalent to r mod m. And it looks weird at first, but the way to interpret this is, well, let's assume I've got my number here, let's 8 plus 4 number, which in our case is 12. So 12 is equivalent, okay, to, let's assume my mode is 9 here. So 12 mod 9 is going to give me the remainder of 3. And this is how we read. So 12 mod 9 gives me the remainder of 3. Or we could also say 12 is equivalent to 3 mod 9. So this is the way we read it. And again, here the m is called the modulus, okay, and r is called the remainder. Now apart from this, you could also write it as, let's say a is my answer, right? Could say a is going to be equal to quotient times the modulus plus the remainder. That's how it is, right? So let's assume I've got 12, okay, let's assume my modulus is 9, okay. Now how can I get a 12? Well, I could multiply it by 1 in there. 1 times 9 plus remainder of 3 would give me 12, okay. We'll also write it in this manner. So here I've got the remainder of 3, okay, this is my remainder. Well, it turns out I could also write it in another way. I could say 2 times 9, okay, quotient here is 2, considering my m is 9, okay, and 9 times 2 is 18. And to get back to 12, I can basically decrease it by 6. See, I could have a remainder of -6, right? And now it is different. It turns out it is not unique. And you can see the trend here. So starting from -6, if I try to write it in ascending order, so -6 to 3, well, from 3 I could basically increase 9 here. So this is going to give me 12. From 12 plus 9, this is going to give me 21, and then so on. And they all behave the same way. I could also go back on the negative number as well. And this is what we call as an equivalent class. Okay, equivalent set, let's say, of 9. Well, in fact, the equivalent set of 9 can have a total of 9 of the sets. Okay, so this is one of the sets. Another set we could have is, let's start with the 4. Well, from 4 plus 9 will be 13, 22, and then so on, and same thing on the back as well. So would be -5 on the back, and then so this is another equivalent class. So for this mode 9, okay, these are the equivalent class of it, and it's gonna have total of 9 of them until all of them is completed. So I've got this 4 here, I can have 5, then it could be 14, and then so on, and same thing in the back as well. Okay, we'll have a total of 9 of them. So if you are trying to find the equivalent set of, let's say, 5, we'll have total of 5 for this 5. So for 5, we start, let's say, from 0 to 5, 10, 15, okay, -5, -10, and so on. And start with the 1 now. So 1, 6, 11, 16, okay, -4 for this -9, and so on. And total of them would be 5, okay, for my 5. So we have, let's do the 2, 7, 12, 17, put this -3 here, -8. If I start with the 3, it's gonna be 3, 8, 10, 18, -2, 7, and so 0 is done, 1 is done, 2 is done, 3 is done. Okay, and we'll have 4, 9, 14, 19, and so on. And on the back as well, we'll have -1. So got this -1, got -6, and then so on. So now this is complete. It contains everything. Okay, now it contains it all. It contains the 0, the 1, the 2, 3, 4. It also contains 5, which means this is now complete, and this is the equivalent set of 5.